So basically, so far we've discussed the internal energy of a system, right? So there's another property of a system that's kind of, in my opinion, probably the most important, and that's the enthalpy. So that's enthalpy, right? And enthalpy, which we're going to call H, is going to be basically defined as H equals the internal energy plus pressure times volume, right? So E is internal energy, P is pressure of the system, and V is the volume of the system. So internal energy, pressure, and volume are all state functions, right? Because they are dependent on state. So when you add up state functions, it would also equal a state function. So enthalpy itself is also a state function, meaning it's dependent on the instantaneous point in time, right? But what exactly is enthalpy? What exactly is enthalpy? So we need to consider a process that's carried out at constant pressure, and that where the only work that's allowed is the pressure volume work, right? So two conditions where we're going to kind of build our equation here. So one is that it's constant pressure, and two is that the work that's allowed is the pressure volume work. So only pressure volume work allowed, which would mean that W is equal to negative P delta V. Okay, so first step in this derivation is that delta E, what's the internal energy? Delta E is Q plus W. So that P is representing the heat at a constant pressure. Okay, so this is heat at a constant pressure. So we can change the W because it's the PV work, right? So delta E is equal to QP minus P delta V. So let's rearrange this such that we can solve for the heat. So QP is equal to delta E plus P delta V. Okay. Now what we're going to do is relate the QP to the change in enthalpy. Right, we're going to relate the QP to the change in enthalpy. Remember the definition of enthalpy was H is equal to E plus PV. Therefore, we can say that the change in H is equal to the change in E plus the change in PV. Notice the distinction between this and this, okay? This is the change of both pressure and volume versus this is P delta V, meaning constant pressure times a change in volume, okay? So since P is constant though, because that's what we kind of determine here, P is constant, that means that the change in PV is only due to a change in volume, meaning delta PV is equal to P delta V. And the reason these two are equal is because the pressure is constant, meaning any change that has to occur in this pressure volume has to be because of a change in volume. So delta PV is equal to P delta V. Okay, so then we can just substitute that into here. So delta H is equal to delta E plus P delta V. Right? So this expression is identical to what we established right here. This is identical, right? So basically, what that tells us is that for any process that's carried out at a constant pressure, which, you know, most reactions are going to be at constant pressure, because if you talk about any reaction that's at sea level, it's going to be at constant pressure, right? It's always going to be that 1 atmospheric pressure. So if there's a constant pressure, any reaction that's carried out at a constant pressure, where the only work that's allowed is the pressure volume work, is the work that's allowed from a change in volume, then delta H is going to equal QP. Okay, and that's a very, very important relationship. Delta H is equal to QP. And in other words, what this is saying, that at constant pressure, where only PV work is allowed, the change in enthalpy of a system is equal to the energy flow as heat. Okay, what this means is that for a reaction that's studied at constant pressure, the flow of the heat is the measure of the change in enthalpy for the system. That's why the terms heat of reaction and change in enthalpy are used interchangeably. That's why, therefore, heat of reaction and change in enthalpy are used interchangeably. Okay? And this is the reason, because it's at constant pressure. All right. So if it's a chemical reaction we're talking about, right? What's more important is that delta H is equal to the enthalpy of the products minus the enthalpy of the reactants. Okay? So in a case where the products of a reaction have a greater enthalpy than the reactants, then delta H will be positive, meaning that the heat will be absorbed by the system. So when delta H is greater than 0, this is heat absorbed by the system. When delta H is less than 0, this is heat expelled from the system, or heat released. Right? And that would this is another way. This is endothermic, and this is exothermic. Okay? So that brings us to calorimetry. Calorimetry. Okay? So this is basically just a device that's used experimentally, kind of to determine the heat that's associated with a chemical reaction. Okay, that's what we call a calorimeter. All right, and calorimetry then is just basically the science of measuring that heat. Okay, so one substance might require a lot of heat energy to raise its temperature by 1 degree, whereas another will exhibit the same temperature change after absorbing only a little heat. Right, and so it's basically this change of temperature, either gained or released, that's more important. Okay, so one thing that's important is that the heat capacity. So what is heat capacity? So heat capacity, we're going to call that C. Okay, of a substance is basically the heat that's absorbed over the increase in temperature. So when an element or a compound is heated, right, the energy that's going to be required is dependent on basically the amount of substance that's present, right? An example of this would be it would take twice as much energy to raise the temperature of 2 grams of water, right? 2 grams of water by 1 degree, than it would take than it takes to raise the temperature of 1 gram of water by 1 degree. It's going to take twice as long, and it's because it's dependent on the amount of substance that's present, right? So when we define a heat energy, or the heat capacity of a substance, the amount of substance must be specified. We have to specify the amount of substance. It's important. So if the heat capacity is given per gram, so if C, which is heat capacity, is given per gram, we're going to call that specific heat capacity. And the units for this are joules over degree Celsius. Degree Celsius times grams, because grams is the most important thing here for specific heat. Or in other ways we can say this is joules over Kelvin times gram. Same thing. It's just a matter of which unit you're using for temperature. Now, if it's given per mole, then we're going to call that the molar heat capacity. This is specific heat capacity. This is molar heat capacity. Okay? If it's given per mole, we're going to call that molar heat capacity. And this is going to have units of joules over degrees Celsius times mole, or joules over Kelvin times mole. Right? So the specific heat capacities of common substances would be basically like water in a liquid state having 4.18 joules over degrees Celsius times grams. I think this is one of the major ones to know. This is a pretty common one. Okay? Now, it's one thing to note is that different substances are going to have different heat capacities, and in certain cases drastically different. it basically takes, if you talk about a certain metal, let's say, for example, iron, iron has a specific heat capacity of 0.45 joules over degrees Celsius times grams, right? So, it obviously takes a lot less energy to change the temperature of 1 gram of metal by 1 degree than a gram of water. It's gonna take more. It's gonna be very easy to do that with iron than it would be with water, right? So it's very, very different with water, right? Basically, what this is something called a coffee cup calorimeter. Okay, how we figured all this stuff out is a coffee cup calorimeter, and this is I think they still do this in many chemistry courses. So coffee cup calorimetry, right? Coffee cup calorimetry. What we're basically doing here is we have two nested, styrofoam cups basically, that's covered through with a stir and like a thermometer, right? And so there's the outer cup that's used for, insulation. So there's an outer cup that's used for insulation. We're going to cover this up. There's a thermometer that's in there. And then there's a stir that's in there. Just make it around like that. So thermometer, stir. So this is covered up like this, right? And there's another cup inside. And that has water. I'll make the water blue. Right, so this is basically coffee cup. The outer cup, right? This outer cup right here is for insulation. It's for extra insulation. The inner cup basically holds the whatever solution. In this case, we're talking about just water. So the measurement of the heat then using the simple calorimeter, right, that I drew right here, is an example of constant pressure calorimetry, because the pressure is going to be constant, and the reason it's constant is because I have it covered. It's lit up. There's a lid on top of it, so it's a constant pressure, right? So this is a constant pressure calorimeter, and this constant pressure calorimetry is basically determining the changes of enthalpy, the heats of reaction for reactions that occur in the solution, right? Remember, in this situation when we had a constant pressure, remember, we call that delta H, the heat equal to the heat of reaction, heat of the reaction, right? So that was the change in enthalpy, and that's what we determined earlier. Okay, so then what we need to talk about was what is the energy that's kind of released. So let's take an example here. What if we had 50 milliliters of 1 molar HCl at 25 degrees Celsius with 50 milliliters of 1 molar NaOH at 25 degrees Celsius in a calorimeter, right? If we put that in a calorimeter. So the reactants are obviously going to be mixed by stirring, and the temperature is going to be observed to increase. So we have a change in temperature. Temperature increases by 31.9 degrees, let's say, okay? So then the net ionic equation, so let's talk about this equation here. It's just basically, I'm not going to go into what a net ionic equation is, but the net ionic equation is essentially just this. All right, that's the main thing that's happening here. So when these reactants, which were at the same temperature, are mixed, the temperature of the mixed solutions is increasing. We see that it's increasing, right? So what that means is that the chemical reaction must be releasing heat. So we're releasing heat because the temperature is increasing. That means the only way that thermometer can pick up an increase in heat is if that reaction actually released heat as energy. Energy as heat, right? So this release energy increases the random motion of the solution's components. It's going to increase the randomness of the solution, which would increase the kinetic energy, which would increase the temperature, right? So the quantity of energy that's released can be determined from this temperature increase, right? But based on this temperature increase, we can determine the actual amount of energy that's actually released. We can so the quantity of the energy release is determined from the increase in temperature, but we also need the mass of the solution, right? And we need the specific heat capacity of the solution, right? So and again, there's a lot of assumptions that are to be made in this, and one of them is that the calorimeter is obviously not going to absorb heat or leak any heat itself. It's just the surrounding. We're not going to be concerned with anything that it does as a system, right? So, and the solution that we're talking about is pure water. There's no impurities to it, and it has a density of, it's just 1 grams per milliliter. And I mean, those are some assumptions that we are making, right? So we know that the heat capacity of water is 4.18 joules, 4.18 joules over degrees Celsius times grams, right? That's a specific heat for water, H2O, right? So let's talk about the energy that's released. So energy released as heat is going to be released by the reaction, right? And so what does that equal? So this is equal to energy as heat, right? That's absorbed by the solution, right? And again, this is just equal to specific heat capacity times the mass of the solution times the increase in temperature, right? Because we said we needed these 3 things to calculate the heat. So in other words, this is just S times M times delta T. Okay, and again, I say S, but it's technically C, right? So in this case, our delta T was 31.9 degrees Celsius minus 25, because 25 is standard temperature. So this is going to be 6.9 degrees Celsius, right? And the mass of the solution is basically figured out from the density. If we have 100, so mass is equal to 100 milliliters times our density of 1 gram over milliliter. So it's basically just 100 grams, or just 1 times 10 to the second grams, right? So then we can just plug and chug and basically figure out the energy. And when all said and done, energy then is equal to 2.9 times 10 to the third joules, right? So then basically, how much energy would have been released if twice the amounts of solution had been mixed? Well, then the answer is basically twice as much as heat would have been produced, right? What that means is that the heat of reaction is an extensive property. The heat of reaction is an extensive property. Okay, what that means is that it depends directly on the amount of the substance. We need to know the amount of substance. It depends on the amount of substance. So, and just to contrast that, an intensive property is basically something that's not related to the amount of substance, right? So an example of an intensive property would be the temperature. So temperature in this case is an intensive property. Regardless of how much amount you have, the temperature is going to be what the temperature is. Okay, so now the enthalpies of reaction, right, the delta H, are often expressed in terms of moles of the reacting substances, right? So the number of moles of hydrogen ions, that's consumed in this reaction, right? So let's talk about that. So it's going to be 50 milliliters, because that's what we, started out with. 50 milliliters times 1 liter over 1,000. We got to get rid of the liters, times 1 mole of H plus over liters. And we get this from the coefficient of the equation, right? We're going to get that from the coefficient of the equation. And this is basically going to give us how many moles of H plus ions are consumed. So 5 times 10 to the negative 2 moles of H plus consumed, right? Meaning that 2.9 times 10 to the third joules of heat were released when 5 times 10 to the negative second moles of H plus ions reacted, right? So then we can figure out the enthalpies of a reaction, and this is basically just a ratio of the two, right? So this would be 2.9 times 10 to the third joules over 5 times 10 to the negative second mole H plus, right? And this is equal to 5.8 times 10 to the fourth joules per mole. This is the enthalpy of reaction, right? So this is the amount of heat that's released per 1 mole of H plus ions that are neutralized, right? So the magnitude of the enthalpy change per mole of the reaction is 5.8 times 10 to the 4th joules per mole. This is the magnitude of the reaction. It's basically a magnitude of the enthalpy change. Magnitude of enthalpy change. Okay? So because we know that heat is evolved in this reaction, right? Another way we can say this is 58 kilojoules per mole, right? And we know that heat is going to be evolved because we released heat, right? So this is going to be negative. So this is delta H is equal to negative 58 kilojoules per mole. That's the enthalpy change, right? So the quick equation for this is Q equals M cat. That's the best way to remember that. Q equals M cat. And that's how you figure out the enthalpy when an object that changes temperature, the heat can be calculated with this equation. Okay. So let's talk about constant volume calorimetry, because this is just constant pressure calorimetry, right? So constant volume calorimetry is a little bit different. And another word for this is bomb calorimetry. So basically, an example of the constant volume calorimetry is those flash bulb flashes in a photograph. And the bulb basically becomes very, very hot, and there's a reaction that happens, and the reaction is exothermic, right? And then the reaction that occurs inside the flash bulb is going to be it doesn't change volume because it's obviously trapped in that shape, right? So under these conditions, no work is done, because if we have a constant volume, that means work is 0, because remember, work was equal to negative P delta V. But if there's no change in V because it's constant volume, this entire equation is 0, right? Then work is not done, because again, volume must be changed for pressure volume work to be performed. So we call this a bomb calorimeter. So basically, we use these to study the energy changes in reactions under conditions of constant volume, right? So again, the energy is going to be the energy change is going to be determined by the measuring the increase in the temperature, right? As always, and in the situation, all that is that delta E, instead of being Q plus W, is just going to be delta E is equal to Q V, and we're going to call it V because it's constant volume, right? So let's, for example, take we have the if we want to measure the energy of combustion of octane. Right? So we want to measure the energy of combustion of octane. Remember, octane is a component of gasoline, right? So if we have a 0.5269 gram sample of octane, and it's placed in this bomb calorimeter, and it's going to have a heat capacity of 11.3 kilojoules. Notice the units, kilojoules per degree Celsius. What this basically means is that 11.3 kilojoules of energy is required to raise the temperature of the water and other parts of the calorimeter by 1 degree. Then the octane is ignited in the presence of obviously excess oxygen, because any combustion reaction requires oxygen. Then the temperature increase of the calorimeter is so delta T is equal to 2.25 degrees Celsius, right? So then how do we calculate the amount of energy that's released? So same equation. So energy is equal to the temperature increase, delta T, times the heat capacity, which is C. And that's how we're going to figure it out. In this situation, we don't need the mass. The mass is not a concern of us. For us, all we care about is the change in temperature and the heat capacity, right? So this energy is going to be 2.25 degrees Celsius times 11.3 kilojoules per degrees Celsius, and that's going to be 25.4 kilojoules. So the key word that you're going to look for in the problem is either constant pressure or constant volume, and that's how you're going to go about it. So this basically means is that 25.4 kilojoules of energy was released, right? Because it's a positive sign in terms of energy. So it's the energy that's released by the combustion of 0.529 grams of octane. So the number of moles of octane that is basically just take the grams, right? This is pretty simple stoichiometric calculation here of octane times 1 mole of octane over 114.2 grams of octane, right? And that's just the molar mass of octane. This is basically 4.614 times 10 to the negative third moles of octane, right? So since 25.4 kilojoules of energy was released for 4.614 times 10 to the negative third moles of octane, then the energy that's released per mole then is going to be 25.4 kilojoules over 4.614 times 10 to the negative third moles is 5.50 times 10 to the third kilojoules per mole. That's how much energy is released per mole. And because the reaction is exothermic, the delta E is going to be negative because it's exothermic, right? So delta E is equal to negative 5.50 times 10 to the third kilojoules per mole. Okay? Because there's no work done, remember this is our equation, delta E is equal to Q plus W. Because we know no work is done, that means whatever change in E that we had is going to be the heat that's involved in this reaction. So Q then is also equal to this above value, negative 5.5 times 10 to the third kilojoules per mole. And that is constant volume calorimetry. We will pick up with Hess's law.